Welcome to Topper HQ, our own study hub. Look, we're not just going to learn about physics today. No, we're going to try to do something a little bit crazy. We're going to attempt to create a new theory from the ground up. I know, it's a huge task, but it all starts with one simple, powerful question that could literally change how we see, well, everything.
Seriously, what if everything you see, space, time, energy, what if it's all just an effect, a shadow of something way more fundamental? Now, this isn't just some random shower thought. This question comes from a very real, very deep crack in the foundation of modern science.
And yeah, that crack is a big one. To be blunt, right now, physics is kind of broken. There's this huge conflict at the very heart of how we understand the cosmos. It's like a battle of two giants.
So in one corner, you've got quantum mechanics. This is our rulebook for the universe at the smallest, tiniest scales you can imagine. We're talking atoms, electrons, all that stuff. And it is incredibly accurate. Then, in the other corner, you have general relativity. This is the heavyweight champ of the big stuff. Planets, stars, entire galaxies. It's also amazingly successful.
So what's the problem? Well, they can't both be right. Not completely, anyway. When you try to use them together, like to figure out what's happening inside a black hole, the math it completely breaks. It gives you nonsense answers. This fight is one of the biggest, baddest, unsolved problems in all of science.
And believe me, it's not for a lack of trying. The absolute greatest minds in history have thrown themselves at this problem. Even Albert Einstein spent the last part of his life searching for a unified theory to connect these two worlds, and he never found it. That's how big this challenge is.
Okay, so if the old roads are all dead ends, maybe we need a totally new path. Let's play around with a really radical what if, an idea that starts by questioning the very fabric of reality itself. Let's see if we can build a universe out of pixels.
You know, we usually think of space as this smooth, empty void, right? It's just the stage where all the action happens. But what if it's not? What if space isn't the stage, but one of the main characters?
Let's give our crazy idea a proper science-y name. We'll call it the Discrete Space Framework. And that word, discrete, is the key. It just means that something is made of separate, indivisible little chunks, instead of being one smooth, continuous thing.
The best way to picture this is to think about the world inside a video game. It looks totally smooth and real, right? But if you could zoom in, way in, you'd see it's all just built from a grid of individual pixels. What if our universe works exactly the same way?
So, in this kind of pixelated universe, space itself is made of these fundamental, unbreakable little units. Time doesn't flow like a river, it ticks forward in tiny, distinct steps, like frames in a movie. Click, click, click. And energy? It's not some separate thing. It's just a vibration, a ripple moving through this underlying grid. And this isn't just science fiction, by the way. This is kind of the core idea behind some real cutting-edge theories out there.
Okay, so that's the big idea. But, an idea is nothing without some rules. Every good theory has a simple, elegant set of rules that, when you let them run, they produce the complicated universe we actually see around us. And these rules, if they're right, have some massive consequences. So let's lay down 3 simple rules for our universe. Rule number 1, there's a minimum length, the size of one of these pixels. Nothing can be smaller, period. 2, information is conserved. The universe's underlying code can't just be created or destroyed. And rule 3, motion isn't really about traveling through space. It's about information hopping from one pixel to the next.
Now check this out. This is the payoff. With just those 3 little rules, we can start to explain some of the biggest mysteries in physics in a totally new way. Gravity? Maybe it's just the fabric of this pixel grid getting warped and bent. All that quantum weirdness? It could be the natural glitches or fuzziness in the system. And a black hole? Maybe that's like a cosmic zip file. It's what happens when you try to cram too much information into one little patch of space.
And if this framework is right, that whole epic conflict we started with just dissolves. Quantum mechanics becomes the set of rules for how individual pixels behave, and general relativity describes what happens when you have billions and billions of them working together. They're not fighting anymore. They're just 2 different zoom levels for looking at the very same system.
It's a pretty neat idea, right? It feels elegant. It feels clean. But this is where we have to slam on the brakes and shift from creative brainstorming to the brutal, unforgiving reality of science. Because in science, a beautiful idea is completely worthless if it can't pass the ultimate test. And this, right here, is the most fundamental rule of the game. A theory can't just explain stuff we already know. To be scientific, it has to make a new prediction, something we can go out and test. It has to stick its neck out and take the risk of being proven dead wrong.
So for our little pixel universe idea, the hard questions are everything. Can we actually design an experiment sensitive enough to see these supposed pixels of space? Does our theory predict some tiny change in how gravity works at super small scales that our current theories miss? And, most importantly, is there any possible experiment that could flat out prove this entire idea is wrong?
Because if the answer to that last question is no, well then what we have isn't a scientific theory. It might be fascinating philosophy, it might be a really cool thought experiment, maybe even great science fiction, but it's not physics, it's just imagination.
And that right there brings us to the ultimate reality check. You know, it's easy and fun to sit here and dream up big ideas. But the gap between a what-if and a working theory of everything is just massive. And it is filled with an unbelievable amount of hard, grinding work.
Real progress in physics isn't just one person having a single brilliant idea. No way. It's about mastering ridiculously deep and complex math. It's about years, usually decades, of focused study. And maybe most of all, it's about having the grit, the resilience to survive being proven wrong over and over and over again. That's the real job of a physicist.
But here's the thing that should give us all a little inspiration. Every single theory we rely on today, from gravity to quantum mechanics, every single one was once just a radical, unproven, kind of crazy idea in someone's head. They all started with a creative leap, but only the ones that survived the brutal testing of reality are the ones that made it into our textbooks. So in the end, the most important question for a scientist isn't just, can I come up with a clever new idea? The question that really drives science forward is this one. Can you design a test so clever, so rigorous, that you can actually prove our current understanding of the universe is wrong? That is where the real adventure begins.